Hey there, welcome back to my series on portfolio allocation using Python. Before we start, I would like to give you a heads up about the fact that the IEX source that we used in the previous tutorial is currently encountering some issues. In particular, after running the code, it will deny the access to the source. If you encounter the same issue, I would instead recommend changing the source of our data reader function to stuk, so that is simply changing IEX over here to stuk. If we then run the code again, it will give another error. This has to do with the fact that the column headers in the stuk source are defined differently compared to the IEX source. One way around this is simply capitalizing the first letters of each closed string over here and over here. If we then run the code again, everything should be settled. There we go. To continue, in this tutorial, I will discuss the optimal trade-off between risk and return. In particular, I will derive the efficient frontier, the cornerstone of mean-variance analysis. To do so, we're going to exploit covariances between our selected financial assets. To derive an intuitive example of this all, I will first derive the covariance matrix. First things first, we need to read in our data. So we say returns is equal to pd.read CSV returns.csv. Then we have to set the index, so we say returns.set index date, and in place is equal to true. And finally, we are able to print the covariance matrix of our returns. The negative covariance between the S&P 500 ETF SPY and the government ETF GUFT over here implies that once one goes up, the other tends to go down. Therefore, by holding both assets, we can reduce the variance of our portfolio. However, this will of course affect the total level of return one is able to acquire. Our goal is therefore to exploit this trade-off, minimize the risk given a target return. To clearly demonstrate the trade-off between risk and return, we're going to create a lot of different portfolios using only our three initially selected assets. In doing so, we determine the historical variance and return of each portfolio. The historical returns and variances will then be used as a proxy for expected future values. Okay, first things first, we have to define our function. So we say define mean-variance analysis graph. We will use the returns that we derived earlier, so we can simply cut returns from here over here, and this we won't use anymore. Then, for the purpose of generating random numbers, we calculate the number of assets in our portfolio. That is the length of our tickers list. So number of assets is equal to the length of our tickers. This will essentially provide us with the number 3, but as a more dynamic input. Furthermore, we create two empty lists, one for our expected returns and one for our expected volatilities. These empty lists will be populated with the returns and volatilities of a variety of portfolios created by assigning random weights to our initially selected assets. Let's therefore call these portfolios random portfolios. We will create 500 of these random portfolios. So we say for I in range 500. And then to determine the random portfolio returns and variances, we first need random weights. When I talk of random weights or weights in general, I mean what share of our invested wealth is allocated to a specific asset. To create these random weights, we're going to use a numpy random function, which produces random floats between 0 and 1. So we say weights is equal to np random, and then we make sure it provides us with 3 random numbers. We should note, however, that our weights should always sum up to 1 or 100%. Our entire portfolio essentially consists out of the earlier specified weights. Hence, we have to divide the weights by the sum of all weights. So that is weights is equal to weights over the numpy sum of weights. Now we are in a position to calculate the portfolio returns. If we multiply the random weights with the expected return of the individual assets and take the sum of all these multiplications, we obtain a portfolio historical return. In matrix algebra, this is exactly the same as multiplying the row matrix of weights by the column matrix of means. So that is portfolio return is equal to the NumPy sum of the returns mean multiplied by the weights. And then we multiply it by 252. In addition, we need to measure the volatility of our random portfolio. Using matrix algebra, we can calculate the variance by transposing the row matrix of weights and multiplying it with both the covariance matrix as well as the weight vector. Then, to obtain the volatility, we simply take the square root. So that is portfolio volatility is equal to the NumPy square root of the dot product between the transposed weight column and the dot product between the returns covariance matrix with their weights. It should be noted over here that we multiply the covariance matrix by 252 to get a year estimation of the covariance matrix as well. Information regarding the derivation of this formula is provided in the description. Finally, we add the results to our currently empty lists. So we say expected returns, append portfolio return. Similarly, we say expected volatilities, append portfolio volatility. Once we run this code, the for loop will recalculate and append the returns and volatilities for 500 different portfolios, each with a unique weight combination of our earlier defined financial assets. We can simply print the expected returns as well as the expected volatilities to get a sense of what is going on in this formula. Expected volatilities, and run the function. Nothing much is going on because I misspecified returns. So over here, returns. There we go. So we essentially obtain all kinds of random returns as well as the associated random volatilities of 500 different portfolios. Before we can essentially use this information in a graph, we have to make NumPy arrays. So we say expected returns is equal to NumPy array of expected returns, and similarly expected volatilities is equal to the NumPy array of expected volatilities. Once that's done, we can create our figure. So we say fig random is equal to plt figure. We will populate this figure with a scatter plot, which requires a specification of an x value, volatility, and a y value, the returns. So we say plt scatter, expected volatilities, the x-axis, and expected returns, the y-axis, and let's say that the marker is equal to a dot. Then we allow for grid lines to be shown, so we say grid is equal to true, and we change the x label to expected volatility, and we change the y label to expected returns. Before actually showing the plot, I will pickle it to be able to reuse and build upon it in tutorials to come. As mentioned in previous tutorials, pickling essentially serializes objects so they can be saved to a file and loaded into the program later on. So we say with open fig random with the attention to write bytes as f, pickle dump figure random f. Alright, let's see whether things worked out by essentially showing the plot. Alright, this looks good. So what we're seeing over here are 500 different portfolios made from our 3 initially selected financial assets. Our eventual goal will be to be on the top of this cone. This is the so-called efficient frontier. On this frontier, we maximize our expected returns given a level of expected volatility or risk. The red dot specifies the minimum variance portfolio. As the name says, this is a portfolio that has the minimum amount of risk or variance. And what's so special about this portfolio is that, in contrast to other locations on the efficient frontier, it does not require any specific expected return input to calculate. It is widely known in the literature that the historical return, which we use as a proxy for expected future return, is more sensitive to estimation error than the historical variance, which we use to proxy expected future risk. Taking this into account, and taking into account that expected return is not an input for the minimum variance portfolio, the minimum variance portfolio is in essence of great influence within finance, taking in mind that it can provide you with a more robust portfolio to work with. So now another question is, what percentual weights do you have to give to selected assets to be on this efficient frontier? Well, that's a topic for next tutorial. Thank you for watching and see you next time.